Hi everyone, welcome to lecture number 7 for Physics 151. The topic for this lecture is free fall. And free fall turns out to be a special case of the kinematics of constant acceleration. So we're going to be using those 3 or 4 equations from lecture number 6. I'll also solve some sample problems from tutorial 7. And as always, you're welcome to stop this lecture anytime, quit the sample problems in tutorial 7 anytime, and go to the online homework number 7 problems that are for credit. Those are all about the case of free fall. So before we say more about free fall, first we need to define what we mean by the situation of free fall. So an object is in free fall when it's experiencing only one force, and that one force acting on the object is the attractive gravitational pull of a nearby planet. Now, the name that we're going to learn later, and that actually was mentioned earlier already in the previous lecture, the name that we're going to learn for this force is weight. So put more succinctly, an object is in free fall when it's experiencing only one force acting on it, and that is its weight. Okay. Now notice an object can have any velocity or no velocity. It could be at rest, at least momentarily, and still be in free fall. Okay, free fall is defined only by which forces are acting on the object. Now, when we drop objects or throw them, near the surface of the Earth in everyday life, there are times when there are added additional forces other than the object's weight that are acting on it. The most common force is air resistance or air drag. So for free fall problems, you're going to see us constantly say at the start of the problem, assume there's no air resistance, or neglect air resistance, or neglect air drag. That's because when you have air resistance or drag on an object, then that's a second force, and then the equations of free fall don't quite hold. Okay, so the answer, the values that we get when we use our equations for free fall are going to be they're going to depart from real life, right? Objects in real life actually travel more slowly than the velocities that we will calculate using our calculations. However, for things like the surface of the moon, where there is no atmosphere and there is no air drag, actually our calculations are really good. Also, before an object is thrown like if it's a baseball or something, before the object is thrown from a person's hand, or after it's caught, or if an object is in contact with a surface, like a ground or a table, like the ground or a table or a ramp, then, or if the object has any other forces like coming from it or acting on it, then those are things that mean that the motion of the object won't follow simple free fall. Okay, so free fall usually applies to a projectile after it's thrown or launched, while it is traveling. We're going to neglect air resistance, but before it lands. Now, here is the sort of what we now call the law of falling bodies. It says that if this is true, if free fall is true for an object, and the object is near the surface of a planet, and I'll say a little bit more about that in a moment, in a couple slides, then the acceleration of that object is constant at all times, okay? And the acceleration has a value that we're going to call little g, and we'll talk in a couple slides, we'll talk about the value of little g near the surface of the Earth. And the direction of that acceleration is always downward toward the center of the planet that's doing the gravitational attraction. Okay, so this acceleration, notice there's nothing in this law of falling bodies that says how massive the object is. So this statement here, that an object undergoes a constant acceleration with a strength of g toward the center of the planet, is true for all objects, regardless of the mass of those individual objects. All they have to do is be in free fall and be near the surface of a planet. In other words, they can't travel like in and out of orbit or something, but they can have any mass. So what that means is that a heavy object like an apple or a stone and a relatively low mass object like a feather, if we get rid of air resistance by dropping this feather inside an evacuated chamber, so this is a little vacuum chamber right here, notice that Once they're released at some initial time, the two objects, right, the massive object, the high mass object and the low mass object, they both experience the exact same acceleration. We can see from this sort of multiple photograph here that they've each traveled the same distance at the same time. There's a classic sort of real life example of this. One of the Apollo 15 astronauts um, dropped a hammer and a feather near the surface of the moon where there is no air drag at all. And the video is only a minute or a minute and a half long. So I recommend that if you open up the slides, you'll be able to follow this link. And I recommend that you take a look at that. Now, the person to thank for the law of falling bodies is Galileo Galilei. And I'm just going to make a historical note here. I like to point out when laws or formulas or things are named after people, it's nice for you to just know who they are and why they have that recognition. Galileo, however, is one of the biggest luminaries in all of physics. Not only did he come up with the law of falling bodies, but he also is credited for not quite inventing the telescope, but making the very first significant observations of the night sky with telescopes. He's also known for several other things. For example, most famously championing the heliocentric model of the solar system, the Copernican model, and trying to overthrow the geocentric model of the solar system, and many other things in the sciences. So Galileo is one of the giants of physics and of science in general. The way he was able to study falling bodies, though, it was a little bit lucky. It turns out if you actually physically drop something in real life, like this apple or this feather near the surface of the earth, this motion happens incredibly fast. And back in Galileo's time, there were no stopwatches, there were no stop motion cameras or high-speed cameras. There was nothing like that. In fact, he didn't even have a good stopwatch or chronometer to be able to time the intervals it takes for things to travel certain distances. So he figured out that if he were to roll a ball down a ramp, he was able to rig up these little bells that the ball would just brush against. So it wouldn't slow the ball down much at all, but it would make the bell ring. And then he could unscrew and reposition these bells in different locations along the ramp. And then he would listen so that the bells would ring at regular, even intervals. It wasn't intervals of exactly 1 second, but the human brain and ear are pretty good at telling when rhythm is regular or beats are regular. So he was able to reposition these bells until, as the ball rolls down, they would ring at sort of regularly spaced timings. And what he noticed is when he did that, he was able to discover that the distance of these bells from the start goes as the square numbers, proportional to the squares, the perfect squares, and the distances between them, therefore, are proportional to the odd numbers, which is just a fluke of the fact that the distances from the start, it's just a number theory fluke. It's really the distances from the start that go as the perfect squares. That is the actual physics, and we'll come back to that in a couple of slides as well. Okay. Now, Galileo was really lucky. He was really lucky that the setup that he chose follows the same rules as objects that are dropped basically straight down, in true free fall. Because notice, this is not a free fall situation, right? There's additional force from the ramp, and of course, there's also mild rolling friction and air drag and other things as well. But mainly, there's this force from the ramp acting on this rolling ball. And plus, the rolling ball itself has inertia, rotational inertia, and things like that. But it turns out he was very fortunate that what he observed was generalizable to the free fall case. If you imagine this ramp getting steeper and steeper and steeper, then eventually what you would have would be an object falling straight down, right? but then the motion of the object would be very fast. So by sort of reclining the ramp, he was able to slow down the motion of free fall to the point where he was able to study it and measure the intervals. Okay, and we'll come back to that in a few slides. All right, back to the more modern understanding and the values that we now know for objects that are in free fall. The value of this acceleration that all masses experience near the surface of the Earth, if we make the free fall approximation, right, like no air drag, the value of little g near the surface of the Earth is 9.80 meters per second per second. So that's the value of that acceleration, the magnitude of that acceleration. And we know the direction of it is always toward the center of the Earth. Now, I want to point out this is the magnitude of the acceleration, right? Meaning the absolute value or the strength of the acceleration. So this is a positive value. Little g is always a positive quantity. So whenever you have a formula that contains little g, like m times little g, for example, make sure you plug in a positive value. In British units, many of our relatives who have taken engineering courses or who simply grew up long ago in the United States, they would have learned a lot more things in British units instead of metric units in their science classes. And the value for little g that they probably know by heart is 32 feet per second per second. So that's just if you convert the metric units into British units. But I recommend that you just sort of memorize this value. I will usually provide it to you as one of our constants, but it's a value you're going to use so often, it behooves you to just sort of learn it. Now, a couple of details about this. It turns out the actual value, the true value of, this is a mean value here, 9.80. The true value of the local value, as it's often called, of little g, of the local Earth's surface gravity strength, varies as you go around the Earth. It's weakest at the equator and it's strongest at the poles. And I'll just leave it as an open question to you if you could think of why that might be the case. There are actually two factors that cause that to be true. It also varies with the thickness and the composition of the crust of the Earth. So it depends if you're on a continent or if you're specifically, if you're in a location of a continent that has a big, dense deposit of rock and maybe metal-rich rock underneath you. So that causes very local variations as well. And then finally, if you were to really increase your height, so if you were to climb a tall mountain, then the value of little g will start to drop just a little bit. It'll probably drop by maybe, a few thousandths of meters per second squared. And then finally, if you were to go above the surface of the Earth, if you were to launch yourself, so up to low Earth orbit, for example, then the value of little g up there drops from about 9.8 down to about 9.0. And then it gets weaker and weaker as you go further and further away from the surface of the Earth. And we'll learn the formula for calculating that when we talk about gravitation. So several chapters from now. For every physics problem where you have to calculate the time of flight or the height, for any physics problem that involves free fall or gravitation, please always use 9.80 for the value of little g. Never ever round off to 10 unless, as we will do later this lecture, we'll do a sample problem, unless you want to make a gross approximation. So if you just want to do an order of magnitude calculation, for example, so it's just very approximate, then a common approximation to use is to substitute 10 meters per second for little g. However, for all of the problems, the numerical problems that you do for mastering physics or for exam problems, it will be expected that you'll be using 9.80. Many textbooks use 9.81 instead. Our textbook uses 9.80, and 9.80 is probably a little more common. If you were to use 9.81, you'd probably still get the same answers to within our significant figures, usually. This quantity, this number of meters per second squared, is often used as a unit of acceleration, and people call that 1g. What they mean is, what's assumed is, of course, that it's on the Earth, right? So people always make the assumption that we're talking about Earth Gs. And the idea is, well, 1g is what we're used to in everyday life. So this is a understandable familiar amount of acceleration. I like to spell it out as GEE myself, and I've seen that used in some printed literature. Our textbook uses just a lowercase g for g's of acceleration, but be careful not to confuse that with grams. So you have to tell from the context of what's going on that that's g's of acceleration and not grams of mass. If you have very sharp eyes, you'll notice grams is never italicized. So it's always written in regular type, regular font, like all other units. Whereas uh, little g is considered more like a variable, right? It's a constant, but it's considered a variable. So it's always written in italics. So people will say things like, "Oh, fighter pilots experience that fighter pilot experienced an acceleration of 5 g's," or the surface gravity on Mars is about 1/3 of a g. Right? The assumption is these are Earth g's. Now let's emphasize something that I said earlier, which is that if an object's in free fall, meaning there's only one force acting on it, which is its own weight, and no other forces like air drag, for example, then the acceleration on it is always a magnitude of g in the downward direction, period. Right? And it doesn't matter whether the object's velocity is going up or whether the object's velocity is going down, or if the object happens to be momentarily at rest, like it is here, turning around between upward and downward. At all of the little snapshots shown here, at all points along this free-falling object's path, we would say that this object is in free fall. This object's in free fall on the way up. This object's in free fall at the top. This object's in free fall on the way down, and therefore its acceleration always has a value, has a magnitude of g, and its direction is always toward the center of the Earth. If we choose the positive y direction or define the positive y direction to be upward, then that means the acceleration has a value of negative g, because it is toward the center of the Earth at all times. So it's a common misconception that the acceleration of an object that is thrown upward, that the acceleration of the object might be positive while the object's on the way up and negative on the way down, or that the acceleration might be 0 up at the apex. No, no, no. Everything I've just said has confused acceleration with velocity. What is positive on the way up is the object's velocity. What is 0 at the top is the object's velocity. And what's negative on the way down is the object's velocity. But what is the acceleration doing all those times? Remember, acceleration is the rate at which velocity is changing. And at all times shown here, the velocity is becoming more negative, more negative, more negative, more negative, more negative, more negative. Always. And that's what's happened. So it's constant. It's a constant negative value for our acceleration. And the rate at which that velocity is changing will always be 9.8 meters per second more negative every second that passes. Let's try graphing this just to take this description, this qualitative description, and make it a little more concrete. So let's start with the velocity graph right here. And we can just see qualitatively, all right, let's call the initial velocity of the object at the moment that it's thrown. So right after the ball leaves her hand, the person's hand, we'll call that V naught, okay? And we can see that if we choose a positive y direction to be upward, we can see that V naught is positive. So I'll give it a positive value up here. As time goes on, at successive intervals, at successive times later, we see that the velocity is still positive, but it's getting smaller and smaller and smaller. So as time goes on, the velocity is doing something like this. Finally, at the very peak, at the apex, then the velocity hits 0. So that's when the velocity happens to hit 0. And then after it passes the apex, we can see that the velocity is negative at all later times and gets to be a bigger and bigger and bigger negative number at all later times. Okay? You might notice that if the object lands or is caught at exactly the same level that it was launched from, then it looks, just from our little sketches here of these vector arrows here, it would look like that the final velocity is exactly equal to negative the initial velocity. It turns out that is true. And it's very easy for us to show that mathematically with our kinematics equations. So if If it just so happens, like in this particular case, that the object is launched and lands at the same level, then it just so happens that this final velocity here is going to be equal to negative v initial. Okay. Now, we know that acceleration at all times needs to be the slope of the velocity graph. Okay. We already know that for an object in free fall, the acceleration has one constant value at all times. So it should just be a straight line like that. Therefore, because this is the slope of the velocity graph, that tells us that the velocity graph must have a constant slope of negative g, and therefore the velocity graph has to be a straight line as well. We also know that the velocity at all times is equal to the slope of the position graph. So just knowing that, we know that the position graph must start with a large positive slope like this. It must have a decreasing positive slope at later times. At this time t right here, if we line up our graphs, our position graph must have a slope of 0 because the velocity is 0. And then our position graph needs to have increasingly negative slopes for the rest of time. Okay? And with the final negative slope being the same magnitude as the initial positive slope. So we can see that our position graph should be something like this. I'll clean it up just a little. This makes a lot of sense intuitively based on what we know the position of this object is doing in the y direction. We know that if we assume, right, if actually, we don't know what this position was right here, but if we just call this y naught, then let's suppose that this is a plot then of displacement instead of position. Okay? Then the displacement is 0 at the start, and if it's caught at the same level, the displacement is 0 at the end. And the displacement reaches some maximum value at the peak. So this is the maximum displacement at the peak. And we can see that the displacement has all the values in between the location that it's thrown from all the way up until we get to the peak displacement, and then it retraces all those displacements on the way back down. Now, one more thing before we leave this example. I want to point out that we actually know what this function is here for displacement or position, and we know what the other function is up here for velocity. I should stick with my velocity color, which is green. All right, so what are those two graphs, or I'm sorry, mathematical functions? Well, think about our equations for constant acceleration kinematics, right? The first equation, equation number 1, gives us velocity, instantaneous velocity, as a function of time. And do you remember what it was? Equation 1 said that v at any time t is equal to v naught plus a times t. That's exactly what this graph is. This looks like a y-intercept and a slope, and it's just a linear graph. And the y-intercept, sure enough, is v naught, and the slope, sure enough, is acceleration, in this case, negative g. So we could be even a little more specifics. In this case, it's equal to v naught minus gt. That's what this graph is. And then what about for that position graph down below? Equation number 2 from kinematics tells us what that is. Delta y at any later time is v naught times t plus 1/2 at squared. In this specific case, for free fall, we know that a is equal to negative g. So therefore, in our specific case, this is equal to v naught t minus 1/2 gt squared, where v naught is a positive initial velocity and little g is a positive quantity. And we remember from algebra that this is a quadratic, right? And a quadratic has a parabolic shape when we plot it. Specifically, this is a downward opening quadratic because it has a negative coefficient on the t squared. So that's exactly what we see here. One of the roots is at t equals 0, and the other root is over here at the time of landing. All right, so great. So it's not a mystery that these graphs have these particular shapes, and these shapes exactly match our algebraic expressions for kinematics under constant acceleration. Let's just do a little more practice with graphing, just using one of the examples taken from our textbook chapter. Suppose that an object is thrown straight up from, is launched straight up from, let's say, the edge of a tall building. It rises up to some sort of maximum position up here, and then it falls straight back down, just barely missing the edge of the building. So, well, I just want to point out that for all of these sort of little graphs where we show the ascent and the descent as being separated from each other, it's actually retracing its exact path as it descends. But we draw it, we make the drawing showing a small separation just for clarity, just so you can see the ascent and see the descent and label things along the way if you wish. So suppose an object is thrown, it's launched, it reaches some maximum height, and then it falls exactly straight back down, but it just barely misses the edge of the building and then keeps on falling after that. Okay. What would the velocity as a function of time look like? What would the position as a function of time look like in those two cases? Well, let's graph the velocity first. Okay. And so first of all, we know if we choose the positive y direction to be upward, then we know that this initial velocity here is positive 15. So this is, let's call this positive 15 meters per second. We see the velocity gets smaller and smaller and smaller. At the time that it passed, that this object reaches its peak, that's when the velocity is exactly equal to 0. So this must be the time at the peak. And then finally, after that, the velocity becomes a bigger and bigger and bigger negative quantity for all later times. Now remember, think to yourself, what should the slope of this velocity graph be? And is it a straight line? Yes. Yes, it is a straight line because we know that the slope needs to be exactly equal to the acceleration, which in this case is negative 9.8 meters per second squared. So it's a constant negative slope at all times for that velocity graph. How about the position versus time graph? Okay, well, if we're going to actually graph position, then we have to define an origin somewhere. And fortunately, they've done that for us. And they've defined the origin at exactly at the start, at the launch point. So let's call the top of the building y equals 0, which means positions above the top of the building, because we've chosen the y direction to be upward, positions above the top of the building are going to be positive, and then positions below the edge of the building are going to be negative. So it looks like we would expect the position of this object to rise until we hit the time of the peak, right? Because time should be the same on all of these plots. So it should rise up until it reaches that time of peak passage. And then we would expect something like this. Is it, by the way, if we did this graph correctly, then it should seem that the slope at all times is equal to what? Right? Is that true? So go ahead and double check that to make sure that the slopes of our position graph here correspond with the values of the velocity at each of those same times. at least qualitatively, right? We're not calculating what the slope actually is. Here's the answer from the textbook. Now, before I get to the quantitative example from tutorial number 7, um, let's do one more semi-quantitative, but also semi-qualitative sort of thought example. It's a very common to have problems or situations where we drop an object from rest. So let's think about that for a moment and investigate what that looks like kinematically. So if we drop an object from rest, then we know that the initial velocity is going to be 0. So suppose that an object is released from, let's say a high building or something like that. This is actually a very high location, right? So a very high cliff. Because I have this object falling well over 100 meters. So that's like more than a football field. All right, so suppose an object's dropped from rest. Then let's also, just to make the numbers simple enough that we can do it in our head without using a calculator, let's invoke that order of magnitude approximation, okay? So again, for any calculated problems, please never use this. Use 9.8 instead. But for now, let's do that. Let's say that g is approximately 10. Then let's ask the question, what will be the object's displacement after 1 second, 2 seconds, 3 seconds, 4 seconds, and so on, right? Or actually after any regular time intervals, but seconds are handy. So let's use individual seconds. Well, we know we have the equation of, we have our equation for position when we have constant acceleration. If I just take y minus y naught, then I get displacement. We can also say we're dropping the object from rest, so we're going to set that initial velocity there equal to 0. So that term goes away. And finally, we'll substitute in what we know for acceleration, which is negative g. And so therefore, this equation simplifies to displacement is equal to negative 1/2 gt squared. And if we plug in g is equal to 10, then that turns out to be about negative 5t squared, right? And that has units of meters for the displacement because we used 10 meters per second squared. So there's units in that. Okay, so notice that the distance that this little object has fallen goes as the square of the time after it's released. So after 1 second, the object has fallen to a displacement of negative 5 meters. After 2 seconds, the object has fallen to a displacement of negative 5 times 2 squared, which is negative 20. 3 seconds, negative 5 times 3 squared, which is negative 45, and so on. Notice that this first quantity is equal to 5 times 1, 5 times 4, 5 times 9, 5 times 16, 5 times 25. So in other words, the distance fallen is proportional to the square of the time that has elapsed. Or put another way, the distance fallen goes as the perfect squares. So the distance that this object has fallen at successive intervals of time follows the perfect squares. So I tried to just summarize that right there. That was Galileo's big discovery with the ball rolling down the ramp. That was what he discovered about the law of falling bodies. Now, Galileo lived before Newton, right? Galileo actually died the year that Newton was born in 1642. So Galileo didn't know why this was the case. It would take much more time before we would have Newton's laws of motion and Newton's general theories about how objects move, and how gravitation works as well. But even still, it was a huge leap forward for Galileo to even figure this out, to be able to eliminate friction or eliminate air friction and everything from his thought process. Because for us, when we drop a heavy object and a light object, like if I drop a rock and a leaf at the same time, it would look like gravity exerts a much greater acceleration on the rock than on the leaf. But that's just because I'm not able to subtract away air resistance in daily life. And you know, for hundreds, thousands of years, people were misled by that. And it was finally Galileo who was able to figure out this general principle that actually gravity is accelerating all objects at the same acceleration. And then later Newton was able to give us more of a theory about why that was true. It just so happens it is a nice fluke of the perfect squares that when you take the differences between the perfect squares, 1, 4, 9, 16, 25, and so on, it so happens that the differences between these just happen to follow the odd numbers, and so on. So if we calculate the differences between these displacements at each of these time intervals, times, we find that the distance fallen during each successive time interval actually follows the odd numbers. So the total distance fallen at each successive time interval follows the perfect squares. But because the perfect squares have this beautiful mathematical behavior, this is what Galileo discovered. And Galileo spent a lot of time chasing down this rabbit hole, trying to figure out what the significance was of the odd numbers and why they were showing up in his measurements with the objects rolling down the ramps. But it's just a nice thing to know. Um, it's a handy outcome. What I would actually prefer that is the first one, which is that the total distance that a falling object has traveled when it falls from rest follows the perfect squares. I want to emphasize this really is only true if the object is falling from rest, right? If the object has an initial launch upward or an initial launch downward, then these intervals won't follow the perfect squares or the odd numbers. Finally, before we just leave this cartoon, I want to ask the question, how would this change if we were to have chosen the y direction in the downward direction instead of upward? Do any of the numerical values change? Do any of the signs change? Okay, so think about that for a moment. Pause the lecture, and then I'll show you. Okay, if we chose the y direction downward, then yes, it turns out that many of the signs of things are going to change. The biggest motivator for that is the fact that now the acceleration is now pointing in the same direction as the positive y direction, because acceleration is always downward toward the center of the Earth. So therefore, the acceleration of this falling body is going to be positive g, positive 10 meters per second squared. G is always a positive number. So, but the question is acceleration equal to negative g or positive g? And in this case now, it's equal to positive g because it's in the direction of the positive y-axis. Okay. In that case, the displacement will always be positive. So all of these displacements now are all positive quantities. But if we were to use this choice of positive y downward to do anything like calculate the distance traveled, okay, or to calculate the time at which the object has a particular speed, those would still all come out to be the same. So anything that doesn't have a directionality associated with it any sort of scalar quantity, if you will, should be independent of our choice of which direction the axis points. You just have to, whatever you define at the start of your problem, you just have to stick to it and be consistent throughout the rest of the problem. And you have to make sure that the plus and minus signs that you attach to your velocities and your accelerations are in accordance with your choice of the direction for the positive y direction. All right, so for an example, I'm going to solve most of problem number 2 with you as an example. And I'll leave numbers 3 and 4 on the tutorial sheet, and number 1, which for you to try on your own. Again, all the solutions are already posted for these. So suppose that we start off with a baseball that is thrown straight upward with an initial launch velocity, if you will, of 25 meters per second. If we choose the positive y direction to be in the upward direction, okay, so I guess it'd be worthwhile for me to sort of draw a little sketch here. If I choose the positive y direction to be upward, then what does that tell me? That tells me that, okay, when this ball is in free fall, we know that acceleration points downward, so therefore the acceleration of the ball is going to always be negative little g, because it's in the downward is opposite the direction of the positive y-axis in this case. Okay. Also, I can go ahead and sort of just sketch for myself what the velocity sort of does. This is the initial velocity, and then we know that as this little ball rises, it should get slower and slower and slower. Eventually, it's going to reach some sort of maximum height, and then it will fall straight back down. If I catch it at the same height, then our story stops there. And if I let it keep falling, then it'll keep falling. Suppose I'm standing on the edge of a building, it can keep falling and keep accelerating after that. So the velocity at later times should be less positive, eventually 0 at the top, the peak. So velocity equals 0. Let me clean that up. Velocity equals 0 at the peak. That's how we know the object is at the peak in this case, right? The vertical component velocity is 0. And then the velocity gets bigger and bigger negative quantities and so on. All right. So what I'm asking initially is, let's make the simple assumption that, that g has a value of 10. In that case, the acceleration in this case will be negative 10. So if we assume that the acceleration is therefore negative 10 meters per second, then after 1 second or 2 seconds or 3 seconds has passed, what would be the approximate velocity of this baseball? Okay, well, remember, this is just reminding us what acceleration really means. It's the rate of change of velocity. So for every second that goes by, we need to make sure that the velocity changes by minus 10 meters per second. So after 1 second has gone by, we can just subtract 10 meters per second from the initial velocity, and that would be equal to 15. And if we subtract another 10 meters per second, then that would be equal to 5. And do it again, and it's negative 5. Notice I can go right past 0, and there's no problem with that at all, right? So if I were to ask you, just looking at this chart of numbers right here, approximately what time does this baseball reach the peak of its arc? You can see that the peak should be what? It's when the velocity was equal to 0. This is a table of velocities. It looks like that would have happened right around here, halfway between 2 seconds and 3 seconds, right? So that's actually going to be one of the things that we're going to calculate in a few parts from now. And this little table right here should be a good sanity check for us. So we should see that the peak occurs, the time of the peak should be roughly 2.5 seconds. Now again, we're using a crude value for little g right now. So when we use a more precise value of 9.80, it won't be exactly 2.5, but it should be in that ballpark. All right, good. That's all. That was the whole point of this little table right here. Now, this is the same baseball with the same initial velocity, okay? And just so you'll match the signs that I've put on all of these velocity values, again, I'm going to insist that the positive y direction be upward. Although if there weren't any multiple choice answers, you could choose your own direction. You could choose it upward or downward. Now, let's answer some of these questions. How could we find the ball's velocity at any fractional time? Okay, well, look back at your table of equations for kinematics with constant acceleration and think about what we know and what the unknown is that you're trying to solve for. So our known values are initial velocity, positive 25 meters per second, and our acceleration, right? Negative 9.8 meters per second squared. And then finally, your time. So time is given in this particular case as 3.8. And what is our desired unknown? We want to know what is the velocity at that later time. Well, is there an equation in our toolbox that has that set of knowns and that desired unknown? I think the answer to that is yes, right? If you think about equation number 1 from kinematics, that should be v is equal to v naught plus at. Sure enough, that exactly gives us what we want. It gives us our desired unknown, and everything else is already known. So let's go ahead and solve. And just to sanity check this, remember, we already estimated that the peak of the ball's path was at around 2.5 seconds, roughly. And this problem is asking us about a time at 3.8 seconds. So it should make sense that the ball should be on its descent already, right? The ascent is done and we've passed the peak and it should be on the descent. Sure enough, good. We have a negative value for the velocity, which is what we would expect. Okay. We also know that the ball probably hasn't passed its starting point yet. By symmetry, we would expect that to happen at roughly 5 seconds. If the peak was at 2.5, we'd expect the ball to pass the starting point at roughly 5. So when we calculate the displacement in the next part, we would expect it to be somewhere between the peak and the starting position. So still a positive value, not a negative value, but so it hasn't gone back past the starting position into negative territory yet. So how can we find the displacement at any particular time? Well, I recommend that you pause for a second, either think from memory about the equations for kinematics with constant acceleration, or look at them. And given the knowns that we all have now for t equals 3 point, the known quantities that we have for t equals 3.8 seconds, what equation could you use to find the displacement? Okay, once again, there are multiple possible correct pathways that you could follow. But one of the ways that you could do it is to use equation number 2, which is, you may have noticed that we've written them with x prior to now. I'm just switching to y because it's traditional to use y for vertical quantities and x for horizontal quantities, but the equations otherwise are exactly the same. Y is just a position, just like x is a position. And in this case, I'm going to convert that into a displacement by moving y naught to the left side of the equation. And the acceleration will be negative g because we've chosen the positive y direction upward away from the center of the Earth. And now we can solve. Good. So the displacement is still positive, which means that the ball is still above its starting position, which is what we expected from our sort of prediction. Okay, let's take a quick look at, um, um, I'm gonna actually, I'll let you solve part D on your own, which is when does the ball return to its initial Y position? So at what time does it pass its initial Y position? We already predicted that it should be around 5 seconds, but that was using a crude value for little g. So you can see all the answer choices are in that general ballpark, but I'll let you calculate it more precisely using 9.80. Let's answer the question, at what time does the ball reach its maximum height? Okay. All right. So once again, when you see maximum height, also known as peak or apex, that is it's a term in plain language, but it means something mathematical, right? Do you remember which quantity that tells us something about mathematically? So you might remember a few slides ago, we talked about how when an object reaches its maximum height in free fall, that's because its vertical velocity or vertical velocity component is equal to 0. Okay? By the way, when we have projectile motion, when something is moving in 2 dimensions, we'll qualify this and say that it's the y velocity that has a 0 component at that moment, even though the x velocity could still be traveling along. But for now, we only have a 1-dimensional case, so all we have is y velocity. So it's fine to omit it, or as you probably saw, our textbook always puts it on, always puts on the subscript. Okay, we also know the initial velocity is positive 25, and we still remember that the acceleration is negative g. So what formula could we use to find time knowing all of those quantities? Well, one of the simplest formulas we could probably use is equation number 1. So the velocity at the peak is equal to the velocity at launch plus a times the time at the peak. Now, I could have called these final velocity and final time, but that might imply like landing or when the ball's caught or something like that. I really want to just make it clear that this is at the peak. So now plugging in the values that we know, we can solve for the time at the peak. Now the next part F, asks what is the maximum height that the ball reaches? So notice that that is at the peak. So one of the things we could use is the answer to the previous problem. We could say, okay, we know that at the peak, time is equal to 2.55 seconds. So that is something that we could treat as an additional known. We know the initial velocity. We also know the acceleration is negative g. Okay. And then maximum height. We know that at the peak, the velocity is equal to 0. So those are all of our knowns. And then the unknown that we're trying to solve for then is the position or displacement. So what is the displacement up at the peak? Well, there's multiple correct ways to proceed at this point. If you choose equation 3 from our kinematics equations, we have that the velocity at the peak squared is equal to the velocity at launch squared times 2 times a times delta y. And that's the displacement up at the peak. That works. If we plug in our values, we can solve for the displacement at the peak. Or if we wanted to, we could use our second equation of kinematics and solve for the displacement that way. So the displacement at the peak would be equal to v naught times the time it takes to get to the peak, because now we know that, plus 1/2 at squared, where that t again is the time at the peak. And if you were to plug those values in, you'd get the same answer. If we use all of these values, this scenario is exactly the same as the one that we discussed qualitatively in the middle of this lecture. So I'm just going to go ahead and reproduce the slides from, or the graphs from that previous slide, that where there was a cartoon of the person throwing the ball straight up and the ball came straight back down. Okay. So we already know qualitatively what these shapes should be, and now we can just label these graphs with a few quantitative values based on all of these numbers that we've just solved for. So if you look back at all the previous parts, we know, for example, that the time at the peak is 2.55 seconds. The time at which the ball passes its starting position, assuming that it could either be caught there, or or can land there, or it could go right past it, was 5.1 seconds. So those are the answers to part E and part D. We know that the peak occurs when the velocity is equal to 0, so 2.55 seconds. And then by symmetry, when the ball passes its starting position, its velocity should be exactly the opposite. Instead of 25 meters per second, it should be negative 25 meters per second. The maximum height reached was 31.9 meters. And finally, the value of the acceleration is negative g. Okay, that concludes this lecture. So I recommend that you try the additional problems in tutorial number 7, check your answers against my solutions, or any time you can leave those aside and go to the online homework problems that are worth credit and try those. Again, all of these problems can be solved with the 3 or 4 equations of kinematics for constant acceleration from lecture number 6 and from the previous 2 parts of the book chapter, of our textbook chapter, from 2.4 and 2.5.